We've pulled together some fascinating material analyses looking at the history, the mechanics, the modern options.
Now let's unpack this hidden world where engineering meets the ocean and see how something so fundamental has undergone such a dramatic transformation.
Let's do it.
Okay, let's start with the absolute basics. Initially, the stern tube was, well, pretty simply the hole where the propeller shaft exited the ship.
Right. Very basic concept.
In the days of early wooden vessels, this wasn't some high-tech marvel we'd recognize today. It was actually incredibly ingenious for its simplicity.
It really was.
The propeller shaft passed through a bore in the stern frame, and the bearing material they used to support that shaft was something called Lignum Vitae.
Yes, Lignum Vitae, the wood of life. And the real genius of it is that it's a naturally oily, incredibly dense wood, so dense it actually sinks in water.
Wow, okay.
And it had these inherent self-lubricating properties when it got wet, so it could function effectively with seawater itself, acting as the primary lubricant and coolant.
So a truly water-lubricated system, just using the ocean.
Exactly, relying entirely on the surrounding water to keep things moving smoothly, or relatively smoothly for the time.
Yeah, it makes perfect sense for those early sort of lower speed vessels, doesn't it? The simplicity, the self-sufficiency, it's undeniable. But I'm curious, what was the biggest practical limitation? What was the Achilles heel of that water-lubricated Lignum Vitae system that eventually forced engineers to look for something else?
That's a great question. While it was simple, its main weakness was its susceptibility to wear, especially from abrasive particles like sand and silt in the water. Think about operating in shallow ports or murky rivers.
Right, it would just grind it down.
Precisely. But then, as you can imagine, everything truly changed with the Industrial Revolution. We shifted from wooden hulls to metal ones.
Okay.
And the rise of high-power steam engines and later diesel engines dramatically increased the demands on these systems. Suddenly, those simple water-lubricated wooden bearings just couldn't handle the new loads, the higher speeds, the sheer power output.
That's stress.
Way too much. The question then became, how do you support a heavier, faster spinning shaft more effectively and reliably for these new, powerful ships?
And the answer was?
The answer was a really pivotal shift, the emergence of oil-lubricated systems. And the profound insight here wasn't just finding a new material, it was a whole paradigm shift in the engineering approach.
Okay.
A key material called white metal, or more commonly Babbitt metal, which is an alloy mainly of tin, lead, antimony, and copper, became the standard for the bearing surface.
Babbitt metal, right.
It wasn't just about it being a stronger material, though. Its properties allowed for the formation of a stable, hydrodynamic oil film. You have to imagine the shaft literally floating on this super thin, almost frictionless cushion of oil.
So no metal-on-metal contact.
Ideally, none at speed. This drastically reduced friction and wear, which meant enhanced bearing life and, critically, vastly reduced maintenance compared to the old ways.
That sounds like a game changer.
Oh, it absolutely was. To manage this, the stern tube became a carefully closed system filled with lubricating oil. This oil was typically kept at a slight positive pressure, usually via a header tank located higher up in the ship.
Why the positive pressure?
Good point. That pressure helps prevent seawater from leaking in and ensures a continuous supply of oil to the bearing surfaces. The system would then circulate the oil, often through a sump to collect it, a cooler to manage the heat generated.
Because friction still generates some heat, even with oil.
Exactly. Even a little friction at those speeds adds up. And then through filters to keep the oil clean. This oil-lubricated setup quickly became the industry standard for most large merchant ships because it was just so reliable and performed so well.
So the shift to oil was revolutionary for performance. But then as an engineer, the immediate sort of monumental challenge you face is, well, containment.
Right, totally.
How do you keep this vital oil in and keep the massive pressure of the ocean out? It's a classic engineering dilemma, isn't it?
It really is. The boundary has to be perfect.
Early solutions were pretty basic, like stuffing boxes, basically packing fibrous materials tightly around the shaft.
Yeah, like packing ropes soaked in tallow or grease.
Yeah.
Very rudimentary.
And I imagine prone to leakage and needing constant adjustment.
Constantly. Not ideal for long voyages or reliability.
So by the mid-20th century, we saw the widespread adoption of something better. Radial lip seals.
Yes, that was a major step forward.
These were typically elastomeric rings, think synthetic rubber, often reinforced with tiny garter springs.
Yeah.
Can you picture like a miniature elastic band that helps the seal lip hug the shaft tightly?
Right, maintaining constant pressure against the rotating shaft, or usually a protective liner on the shaft.
And they were often arranged in multiple rings, right, for redundancy.
Correct. Often 3 or 4 rings facing inwards to keep the oil in, and maybe 1 or 2 facing outwards to keep the seawater out. You might recognize big names like SKF Marine, Wärtsilä, who became major suppliers.
Okay. But as demands kept increasing, bigger ships,
Yeah.
more power, even more advanced solutions were needed, I guess.
Yes, particularly for larger shafts and higher pressures. Later advancements brought us face seals, which are also known as mechanical seals.
Mechanical seals, right. How do those work?
Instead of a flexible lip, these use 2 precisely machined, ultra-flat faces, one stationary attached to the stern tube housing, and one rotating with the shaft. These faces are held in incredibly close contact by springs and hydraulic pressure, creating a very, very narrow gap that's lubricated by just a thin film of the oil itself.
Wow, that sounds precise.
Extremely precise. Face seals offer superior sealing capability, especially under pressure, and generally have lower friction compared to lip seals. So, what this all means for the ship's operation, it means robust, reliable sealing became absolutely foundational.
Yeah.
Without effective seals, the whole concept of reliable, long-lasting, oil-lubricated systems just wouldn't work at the scale we see in modern shipping.
It underpins everything else.